Welcome to lesson 15, where we will be adding and subtracting with scientific notation. This is again kind of a lengthy lesson, so just bear with me as we navigate through all the activities. We'll be adding and subtracting scientific notation to answer questions about animals and the solar system. To be successful at this lesson, you will be able to add and subtract numbers given in scientific notation. We start with a number talk with non-zero digits. You're given 4 different expressions. Take a moment to pause here and mentally decide how many non-zero digits each number will have. Now that you've had some time to work, let's discuss. So in this first one, we can think about it as 6 times 10 to the 16th if we apply some of the things that we've discussed in previous videos. If we were to write that out, it would look like this, meaning that we would have only one digit that is not 0, and that would be the 6. In this next one with division, we can rewrite it to look like this. If we work that out, it would be equal to 1.5 times 10 squared. That 10 squared moves the decimal place and adds zeros. So this is equivalent to 150, which means we would have 2 non-zero digits. In this next one, we're going to look at this in 2 different parts. Think about this first piece, the 3 times 10 to the 9th. This tells us that the first digit is going to be a 3. Looks like this. The 2 times 10 to the 7th is going to tell us that the third digit in our answer is going to be a 2, because when we add it to the first piece, you can see then you have the first digit a 3 and the third digit a 2, giving us 2 non-zero digits. In a similar fashion, we're now going to look at this with subtraction. So here's what it looks like written out. Subtracting, and we end up with this value where you now see we have 3 non-zero digits. So keep in mind how those exponents change the place values that you have, and you'll kind of see this play out in some of the activities later on. When multiplying and dividing with scientific notation, the exponent rules involve multiplication and division, which make it a little bit easier. Now that we're going to be adding and subtracting with scientific notation, the exponent rules don't involve those operations. In our next activity, measuring the planets, Diego, Kieran, and Claire were wondering the following. If Neptune and Saturn were side by side, would they be wider than Jupiter? They try to add their diameters together, which are 4.7 times 10 to the 4th and 1.2 times 10 to the 5th. Each of them approached it differently. Pause here to read through each of their approaches, and then we'll come back to discuss whether or not their approaches work. Let's start with Diego. When we add the distances, we will get 4.7 plus 1.2 equals 5.9. The exponent will be 9. So the 2 planets are 5.9 times 10 to the 9th kilometers side by side. This is actually incorrect. Their decimal places do not match based on what he's done. Now, this might make a little bit more sense when we look at Kieran's method as to why Diego's doesn't work. So Kieran actually writes these out. He writes it out as 120,000 plus 47,000, which gives him 167,000. This is correct. Kieran correctly added the 2 distances, but his answer is a little bit harder to compare to the width of Jupiter because it's not in scientific notation. So now you could kind of see, because of writing that out, you can see how Diego's method did not work. We then go to Claire, who says she thinks you can't add unless they are the same power of 10. So she changes the powers of 10 to 4.7 times 10 to the 4th, and then 12 times 10 to the 4th to get 16.7 times 10 to the 4th. So she did do this correctly also. Her answer is also a little bit hard to compare to the width of Jupiter because hers is not in scientific notation either, right? Scientific notation means that that leading factor has to be greater than or equal to 1, but less than 10, and hers is 16.7. So she would need to change that to really make a better comparison. So Kieran and Claire's approaches are alike. They both reached the same sum by attending to the place value, where Diego did not do that. The only difference here is now we want to really think about putting it into scientific notation to make that comparison. So in question 2, we actually go ahead and do that. Jupiter has that diameter of 1.43 times, that should say 10 to the 5th, which is wider, Neptune and Saturn put side by side, or Jupiter. So let's do this comparison. Here's what we know about Neptune and Saturn. Here's what was changed in that last piece that we looked at. And we're going to change that to scientific notation and write that as 1.67 times 10 to the 5th. That makes it easier to compare to Jupiter. And now we can see that Neptune and Saturn combined is greater than Jupiter. The terms must have the same power of 10 in order to be added. So again, our criteria is to be able to add and subtract numbers in scientific notation. We just got a little bit of an introduction there. We're going to continue working through these activities so we can walk away being successful at this. We go into the third activity, a celestial dance. You're going to use this table to answer the two questions. Remember what we just discussed about adding to help you be successful in this activity. Pause the video here to work through these questions and then we'll discuss. Okay, so when you add the distances of Mercury, Venus, Earth, and Mars from the Sun, would you reach as far as Jupiter? So let's go through this. So we have the distances from the Sun column that we're looking at, specifically at Mercury, Venus, Earth, and Mars, and we're comparing it to Jupiter. So I'm going to just list these out on the side here for us to look at. And notice that all of them have are raised to the power of 8 besides Mercury. So again, we cannot add those leading factors together unless they all have that same power of 10. So we're going to go ahead and change Mercury to be written with a power of 10 that has an exponent of 8. Now we can go ahead and add those leading factors together. So you can see them listed out there, still multiplying them all by 10 to the 8th. This gives us 5.409 times 10 to the 8 kilometers, which is less than the distance from the Sun for Jupiter. So no, you will not reach as far as Jupiter in this situation. We next are to add all the diameters of the planets except for the Sun and decide which is wider, all of these objects side by side or the Sun. So looking at these diameters, we are looking at Mercury, Venus, Earth, Mars, and Jupiter and comparing it to the Sun. So I'm going to list these out again. And again, we don't have all the same powers of 10, so we want to do some rewriting here to make sure we can actually add those leading factors together and then multiply by a power of 10 that they all have in common. So we're going to go with changing these to have an exponent of 4. You maybe did it a little bit differently. It shouldn't matter if you maybe chose to change them to 3 or maybe 5. That is totally fine. I decided to change it to 4 because I saw I had an exponent to the left of 4 and an exponent to the right of 4. So that was just my justification there. So I'm going to change Mars and Jupiter as well. So you can see that all of those have now been rewritten to have a exponent of 4, which means I can now add together all of those leading factors, still multiplying it by 10 to the 4th power, which gives us 17.7363 times 10 to the 4th. That is not in scientific notation. So if we were to go ahead and write that in scientific notation, that first number has to be greater than or equal to 1, but less than 10. That does change our power of 10 to be 10 to the 5th power. So with that being said, that's less than 1.392 times 10 to the 6th, which is the Sun. So the first 5 planets side by side are not as wide as the Sun. And you see that because of that exponent of 6, right? So that kind of takes us back into the warm-up activity when we really thought about those place values and where things fell. Here's what it looks like if you wanted to put it into perspective and see a scale drawing. Okay, in this last activity, we are going to be looking at Old MacDonald's massive farm. And we again have another table that lists a variety of different creatures, including humans, including bacteria. Just keep in mind as you're answering these questions that a conjecture is an opinion or a conclusion based on incomplete information for question number 2. So it's kind of opened for possible answers just based on what your conjecture is. Pause here and work through those 4 questions, and then we'll start to navigate them together. Okay, so question 1 gives you a variety of different creatures that they're asking you to find the total mass for. So they do ask you about cows, sheep, chickens, and humans. And they do give you different amounts of each of those. So I think it's just 1 cow, 2 sheep, 3 chickens, and then a farmer. So we're going to just list these out. We know that there's just the 1 human. There is just 1 cow. There's actually 2 sheep. So we're going to actually double this. So using our multiplication rules, we'll just do 6 times 2 here. And chickens, there's 3. So 2 times 3 gives us 6. And still multiplying by those powers of 10. Okay, so again, we have to have the same exponent if we're going to add these together. So we're going to rewrite these to all have a power of 1. So we're going to change the cows to 40 times 10 to the first. The sheep will stay the same, and the chickens will be changed to 0.6 times 10 to the first. We can now add together all of those leading factors. And that's going to give us 58.8 times 10 to the first. So altogether, they weigh 588 kilograms. That is their total mass of all of those. In the second question, we are making a conjecture here about how many ants might be on the farm. We're going to just, again, this is an opinion. If you look at the ants here, you can see that information, but we're going to just suppose that there's about 10 to the 6 ants on the farm. So again, that's my conjecture. Yours might have been different, but the process should still remain the same. So that means we are going to multiply the 10 to the 6 by the mass of the ants, which is the 3 times 10 to the negative 6. And then that would tell us that there's 3 kilograms. Then the new total would be 591. So again, a conjecture. So whatever you chose to make your conjecture about in terms of the number of ants in the farm, you would replace what's highlighted in yellow with your value, and then the rest of your numbers would change based on what your conjecture was. Question 3 asks us the total mass of a human, a blue whale, and 6 ants altogether. So we have a human, blue whale, and 6 ants. We're going to write those out again. So we have 1 human, 1 blue whale, and 6 ants. So that's what that would be written out. And then I'm going to do this one a little bit differently. I'm going to actually write out their decimal value. So humans would be 62. You can see the decimal value for the ants here and the blue whales here. I'm going to just move that 62 down so we can kind of align things and add them together to see the total kilograms, because they are asking for that exact total altogether. Now, just keep in mind those place values again, because that's going to allow us to strategize for question number 4 and come up with the best answer. Question 4 asks which is greater, the number of bacteria or the number of all other, it says animals, we're going to just say all other creatures in the table put together. Now, I want you to specifically look at the zooplankton, and we're focusing in on the exponents. So the bacteria is 5 times 10 to the 30th. We know that's a very, very, very large number because it's a positive exponent. The zooplankton is 1 times 10 to the power of 20. Now, if we write that out, here's what bacteria looks like. Here's what zooplankton looks like. Already, I could see that the bacteria is much larger than the zooplankton. So there's really no need to add all of those creatures together, because look at the remaining exponents. All of those remaining exponents are less than 20, which tells me when we add all of those together, that kind of goes all the way back to the warm-up where we looked at the non-zero digits. This tells me that the number of bacteria is greater than all of the others combined. You simply will not get a number larger than the than the bacteria when you add everything into that zooplankton that we've listed out. So overall, you are successful at this lesson if you feel you can add and subtract numbers given in scientific notation. Read through that lesson summary if you would like to. Otherwise, that is the end of this lesson.